Hello, welcome to a stable matching conceptual overview walkthrough. So what is stable matching? So the problem is given a set of n jobs and n candidates with some preference list. So for example, if we had candidates Anita, Bridget, and Christine, and we had jobs Apple Incorporation, Banana Corp, and Cherry Inc., then we have also the preference list for both the jobs and candidates. So for example, Apple has their Anita as their first choice, Bridget as their second choice, and Christine as their third choice. So now that we have a preference list for both jobs and candidates, how do we pair the jobs and candidates such that we avoid rogue pairs? A rogue pair is a job and candidate who wants to work together over their current matching. So if we had the pairs Apple and Christine, along with Banana and Bridget, then we can see that Apple prefers Bridget over Christine. Bridget is their second choice, and Christine is their third choice. And we can also see that Bridget prefers Apple over Banana. Apple is their first choice, and Banana is their second choice. Because of this, Apple and Bridget will run away together to form a rogue pair, even if Banana and Christine are already satisfied with their pairing. So for Christine, Apple is their first choice, so they're satisfied with their pairing, and we can also see that Banana's first choice is Bridget, so they're also satisfied. So how can we avoid rogue pairs? We will use the propose and reject algorithm that proceeds in days to understand how it works. So the algorithm follows a format such that every morning, each job proposes to their most preferred candidate on his preference list who has not yet rejected this job. So every afternoon, each candidate collects all the offers she receives in the morning, and she chooses the job offer she likes the best, and she rejects every other job. All right, so what is the goal of the algorithm? So there are two goals. We want a stable matching for all jobs and candidates such that we have no rogue pairs, and that is our second goal. So what is the example of our algorithm working? So based on our example, we can denote that the jobs are proposing to our candidates. So for example, on day 1, Apple and Cherry will both propose to Anita on day 1 because Anita is their first choice. Banana will propose to Bridget on day 1 because Bridget is their first choice. Because Anita had more than one job offer, she will choose the one offer that she likes the best, and she will reject every other offer she receives. Because Apple is their first choice and Cherry is their third choice, she will choose Apple over Cherry, and she will hold on to Apple's offer onto the next day. So on day 2, Anita still holds on to Apple, Bridget still holds on to Banana, and Cherry, because it was rejected, will go on to their second choice, which was Bridget. So now Bridget has now 2 offers, and she will choose the one she likes the best, and she will reject every other offer. Because Cherry is their third choice as well, Bridget will reject Cherry, and now on day 3, Cherry will move on to the third choice, which was Christine. And because every job and candidate are now paired, we will end the algorithm. So the propose and reject algorithm will always output a stable matching and will always halt. So why is propose and reject stable? So given that we have 2 pairs C and J, and C star and J star, there are 2 conditions needed to form a rogue pair. So if J star prefers C over C star, J star must have sent an offer to C according to the algorithm and got rejected over J. It is not possible that C prefers J star over J, thus we have no rogue pairs. So our second condition is if C prefers J star over J, J star must have sent an offer to C star before C, and therefore never received an offer from J star. Since C star is satisfied with J star, there are no rogue pairs. So why does the algorithm halt? Well, the best case is every candidate receives an offer on day 1 and the algorithm terminates. So the algorithm terminates on day 1. The worst case is every job gets n-1 rejections, and the nth candidate receives the job that got rejected by every other candidate, which means it took n times n-1 plus 1 days. So the example of a worst case scenario is if we had 5 men and 5 women, and the men propose such as in a dating show. Given that we have these preference lists, we can see the worst case play out. So now that we have the females and male preference list, we can run the algorithm to find that no woman can receive more than n proposal, and once every woman receives a proposal, the algorithm stops. Therefore, in the worst case, every woman except for one receives a proposal from every man, and the last woman will receive one proposal on the last day and ultimately end the algorithm. So in our above example, 4 men end up with their fourth preference and 1 man with his fifth preference. And thus we have 21 days in our runtime for our algorithm, which is also the worst case scenario. So as the algorithm progresses, each job's options get worse, while each candidate's offer improves. This is denoted in the improvement lemma. So if job J makes an offer to candidate C on the case day, then on every subsequent day, C will have an offer that is better than or equal to their preference for J. So another thing we have to note from stable matching is there's optimality. So note that there could be multiple stable matchings. So we call a matching job optimal if every job is paired with their optimal candidate. A candidate optimal matching is the opposite, where each candidate is paired with their optimal job. So given that we have the example of Anita, Bridget, and Christine, so when we ran the algorithm with the jobs proposing, we get Anita apple as a pear, Bridget banana, and Christine and cherry. Because the jobs we're proposing, we say this matching is job optimal or candidate pessimal. So if we flip it around where the candidates do the proposing to the jobs, we can see we get a different stable matching. So we get Anita banana, Bridget apple, and Christine and cherry. Because the candidates propose this time, we can say this matching is candidate optimal or job pessimal. So how can we show if there's only one stable matching? So we run the propose and reject algorithm with jobs proposing and run again with candidates proposing. So if the stable matchings are the same, then we found a job and candidate optimal pairing. All right, so let's get on to the worksheet. So on question 1, it says, suppose the stable matching algorithm is run on a set of jobs and candidates. So it's asking us whose prospects gets better over time and whose gets worse. So if we recall from the example of Anita, Bridget, and Christine, then we can say that the candidate's match prospects gets better over time. Because when Anita received an offer from both apple and cherry, then she rejected cherry because it's their last preference, while apple is their first choice. According to the algorithm, if later on she receives a job that is better than apple on her preference list, she will choose that job over apple. So in the case, as the algorithm goes on, Anita will choose a job that is better over time. So what about the jobs? Well, we can denote from the example where cherry got rejected by Anita, their first choice, and then got rejected by Bridget, their second choice, and then they had to be satisfied with Christine as their third choice. So we can say the jobs match prospects gets worse over time. So part B is asking us to try to prove our claim in part A based on the improvement lemma. So we can try to use proof by induction. So if you recall, proof by induction needs 3 things. We need a base case, inductive hypothesis, and an inductive step. So the base case is on day I equals K. We can say that candidate C receives at least one job offer, and at the end of the day, candidate C will either keep job J or chooses a job she prefers over J, or also noted as better than J. So if we believe that the base case holds, we can do the inductive hypothesis, which says suppose the base case holds for some arbitrary day I is greater than or equal to K. So the inductive step is trying to say that we want to prove the case for day I plus 1, because if we prove that the next case works, then that means every other day will also work as well. So by the inductive hypothesis, on day I, C had an offer from J prime, which they like at least as much as J. So what is J prime? So J prime is either J itself or a job better than J. So based on the propose and reject algorithm, J prime proposes to candidate C again on day I plus 1, and our candidate will also may receive other job offers. C will choose J prime or a job better than J prime on that day, and we know that J prime is already a job that is at least as good as J, and thus the case holds for day I plus 1. So thus we have proven that the improvement lemma holds. Part C is asking us to try to prove termination. So in the case of this is what if a job was unpaired? Because if a job was unpaired, the algorithm will never terminate because the algorithm only terminates when every candidate and every job are paired. So suppose through contradiction there is a job J who is left unpaired at the end of the algorithm. J must have proposed to every candidate and got rejected by every candidate. Thus they had been left unpaired. So this means that every candidate had a job they liked over J, because in the case if they did not hold an offer, then if job J proposed to that candidate, the candidate will hold on to job J's offer. So in order for J to be left unpaired, then every candidate must have had a job they preferred over J, thus they rejected J. So thus there were n jobs and n candidates, not including J. So because if we're including J, that means there must be n plus 1 jobs in total, and this case contradicts that we only began with n jobs. So the algorithm must have terminated. So part D is asking us to prove stability. So what if a job formed a row couple? So if we had CJ as a couple and C star and J star as a couple, then one case to form a row couple is if J prefers C star over C. C star must have preferred J star over J such that C star J cannot be a row pair. Because J or J star can either propose to C star first, C star would have hold onto their offer, and once the other job proposes to C star, then C star would choose the best job. Because C star chose J star over J, that means J has to be satisfied with C. So the other case is if C star prefers J over J star, so J must have proposed to C first and never proposed to C star. Thus C star J can form a row pair. Because if C star prefers J over J star, if J ever proposes to C star, then C star would have held onto J for the remainder of the algorithm. Thus, J would never have proposed to C. But since C and J are a pair, J must have proposed to C first. Alright, so hopefully this was a helpful conceptual overview of stable matching.